So, as Dr. Cracow said, it will be the presentation about photovoltaic spectroscopy. So, I would like to first give a few words about current photovoltaic cells that we know from the market. So nowadays, the most commonly used semiconductor that is used in photovoltaic cells is, of course, silicon. It takes about 95% of current market of the photovoltaic cells. And we know very well three main technologies to produce photovoltaic cells. It's monocrystalline, polycrystalline, and thin films, from which the polycrystalline is now the most common used, as it is cheap to produce, and is quite efficient. Average current efficiency of the photovoltaic cells is about 15 or 20%. But the demand to have cheap and to have energy that is easy to produce is big. We want to have another solutions and other technologies to produce photovoltaic cells. So the growing demand for the clean energy pushes the market, pushes the researchers to look for new materials and technologies. But first, maybe we will ask the question, what is the ideal photovoltaic cell? So it must be cheap to produce, clean to produce. It must have quite high efficiency. We want to have high quantum efficiency, and also we would like to have a cell that produces a lot of current from a small area. And of course, durability, because we want to use it for a long time. And flexibility in application, because we want to have cells that we may use in everyday life or everyday devices to supply them. And also, you must need to take account that cells, we want to have them clean, so we want to have them or recyclable or easy to utilize. So we have currently some new technologies that are emerging from the market, on the market. First of all, it's good to know that perovskite. This is the solution that is currently, in fact, successfully introduced to the market. We have some solutions that are available. The very interesting technology is quantum dots, which enables to produce materials with adjustable band gap. So it's quite interesting. Another one is multi-junction. It's in fact not very cheap in production, but it gives opportunity to produce current from the very wide spectral range, so efficient use of the energy from the sun, and also some organic solutions. And we would like to research the new solutions. We need to make a possibility to characterize the photovoltaic cells. So what is the most important is, of course, quantum efficiency, internal and external. In fact, the ideal cell would, of course, produce from each photon that incident the cell a carrier. So we would like to have this ideal cell, but of course it's not possible. So we would just need to research the materials, the solutions, the technology that will maybe approach this ideal situation. And of course, as I previously said, photocurrent and the density of the current from the area. So the demand to find these solutions pushes also the demand to have some good quality systems that enables to measure these characteristics, to research for these new technologies. So we just now may ask the questions, what the characteristic of the system must provide to give the opportunity to make appropriate research. So we just need to have stable measurement conditions. We want to be independent of the, environmental changes or something. We just want to explore the possibility of the material, of the technology, for a full solar spectrum that is available outside. We need to have a possibility to measure. It is advisable to have a possibility to measure in one system, by one system, many kind of samples. Because when we research, we just make a lot of samples that are maybe different technologies. So it's good to have a solution that will provide adjustability to make these measurements on very different samples. And what is quite important also, it's a possibility to simultaneously measure all the needed parameters. So it's another kind of aspect that provides us stable data that we measure in a stable conditions in the same time, so the sample has not changed during we have our measurements. And of course, easy and automatic operation is a very good characteristic because it makes us not too involved in the manual operation. So, I would like to introduce our solution, our system to measure, to research photovoltaic cells technologies. So this is how it looks. We have a big sample chamber. This is the interior of the sample chamber. And I will go to the details, starting from characterizing the system. So as I previously stated, one of the most important things is stable conditions of the measurements. The most important thing is incident light here. We need to have a stable incident light, a stable power of the incident light, but also it's good to have it adjustable. We want to measure in full spectra, solar spectra. It's available in our system. The system provides either illuminating the sample with the monochromatic light or with white light. And the beam is in a stable size. It's 1 centimeter square, so it's quite stable. To illuminate the sample, we use in fact 3 lamps in 2 kinds. Here we have a monochromator, which has 2 input slits. On the one, we have a xenon lamp here, and the halogen lamp. Here we have the spectra, so we see that we cover all the solar spectra that we want to research. And also we have another xenon lamp with air mass filter, which enable us to measure cells that are in simulation illuminated with the white light of the sun. So we can make measurements in with monochromatic light, and also in conditions of that mimic the sunlight outside. What's important here maybe to notice that the monochromator works automatically. So it's equipped with 3 types of gratings and also a mirror. So from the monochromator we also can have white light, and it all works automatically. What is important is sample placement here. To place the sample in the system, we use automatic XY vacuum table. And this enables to make the stable conditions of the placement of the sample, and also provides enables to put samples with different sizes, different thickness, any kind of sample that we need. And also it's easy to make some adapters when, for example, we have a sample that have contact pins on one side, on the top or on the bottom. So this is our table. And what is also important to notice that it uses vacuum. So the placement of the sample is very stable. It won't move during the measurements. The table is also movable, and it also works automatically. So it enables to measure the sample in different points and to even testify its homogeneity. So it's quite. It gives opportunity to examine the sample quite in details. And also important to mention is that we have here golden coating, so it provides very good electric contact to have our measurements. Okay, so the measurement system consists of 3 types, in fact, main components. One of them is potentiostat, which was yesterday very well explained by Dr. Karkuszewski. So I won't tell a lot about this. We also have, so this is equipment that measures, of course, photocurrent. And we also have integrating sphere with dual band photodiode. It enables to measure reflectance of the sample. And beneath the sample, on the surface of the table, we mounted another dual band photodiode that enables to measure the light that is transmitted through the sample, if it transmits some light, of course. We have a third photodiode, the same kind, that gives opportunity to monitor actual incident light power. So we have very stable conditions. We monitor all the conditions simultaneously, and we measure photocurrent. We can measure photocurrent, reflectance, transmittance, and also the actual incident light that incident the sample in the same time. So that is a very big advantage, I suppose. Of course, all these photodiodes may be easily calibrated via our software. So it's in fact advisable to make this procedure by the user from time to time. Okay. So here we can see the glimpse of the measurement that we produced with the system. Here we see the value of the current that we observed in time scale. We can see the shutter working, because the system works like with shutter that cuts the light and gives the light to the sample. And then we can also see the resulted photocurrents versus wavelengths. So we see the characteristics of the sample. And the last picture that I want to show you is the view of the photocurrent in different points. So we use this opportunity to move the sample with our table and to see the photocurrent that is produced by the light in different points of the sample. So if you have any further questions, I advise you to ask them. Maybe we can show it with the system that is mounted in another room. Thank you very much.
I have a question. If you have this mirror in the monochromator, why you need the third lamp? Can't you use this xenon lamp and just put some movable filter in front of it? I mean, after the... Yes.
Okay, first of all, this question is loaded. Why is that? Because the idea to mount those mirrors in our monochromators came from Professor Kuntsevich. So it is not our greatness, it is her doing. And The thing is that you really, in this solar simulation made by extra xenon lamp, you are really doing something else. It is not for analytics, it is to provide a bias to your sample. Because you don't want to learn just how efficient your sample is when there is little light, monochromatic light coming on it. It is how efficient it is when it is biased with lots of light. So this is why you have this second extra xenon lamp, and you cannot replace it with the monochromator. However,
with mirror also you cannot. You have all the power, yeah. You have all the light coming from.
no, but you have to have at the same time the white light and the monochromatic light during the measurement.
Ah, at the same time.
Yeah,
Okay.
they are all
Okay,
simultaneous.
I didn't know that.
Okay. Okay. Sorry.
Thank you very much.
Look.
Zbyszek, I can't ask this question. It's about the previous presentation and the first presentation from today. Do you plan to combine the idea of camera with IP, EMS, EMPS, EMVS system?
It is already there. Oh, sorry.
Yeah?
Sorry.
Okay, it was not presented, so.
It is already there because you see this magic sample chamber. It has this fitting here at the back. You can have a camera attached, or you can have potentiostat attached at the same in the same receptacles. If you wanted them both to be attached, we can do it for you at no time. But they are already equipped for this kind of
Okay, so
application.
in the EMPS, EMVS software, you can do the procedure for camera. The problem
No,
is, what do you
it
feed
is
into
in the same program. Yes, you can perhaps we can show it. Panie Grzegorzu, may we see the software? Yeah, you can run. You can attach them both, and then in the software, can we go to experiments, please? And you can see that you can here you can run your EMPS, EMVS, and at the same time, I mean not at the same time, but then you can select the where is it? Impedance camera measurements. So it is all handled by the same software. You don't have to switch between this. If you wanted to do it at the same time, I don't know if it would make sense. But perhaps
No,
you
no,
can do it.
probably I use wrong words. I mean the algorithm for doing EMPS.
It is exactly the same. It is exactly the same already.
So you do not, if you do the EMPS, EMVS, do you scan different frequencies of the light modulation? Or you do what you have in the...
I understand now your question. Okay, with the EMPS, EMVS, we just use one frequency at the time. And yes, we could have this multiple frequencies applied to the system and do the same type of analysis. However, even with the one frequency, we don't do Fourier transform. We do the analysis as I showed for impedance camera, and there is nothing to prevent us to apply multiple frequencies. However, we are at this stage of development that even with one frequency applied, we have nice results. I mean, not we, but actually Dr. Olejnik here, it will be presented. And yeah, and thank you for those questions, because I don't know if Mr. Homiuk mentioned it during his talk, but Professor Ryż is the reason why we have EMPS, EMVS in the first place, because he asked us to build it. So, and he never bought one. So this is how I learned that competition that builds those EMPS, EMVSs gives application nodes that are full of those transfer functions. So meaning that they are really aiming at linear systems, not into And in our case, you may have seen it already that we have harmonics already included and intermediate frequencies that will be included too. I'm sorry for taking you space. Okay.
Just maybe continuation of the question, but maybe it is possible to use light and the impedance camera, like together.
Well.
I mean, actually, you shown this result, yes, that you have modulation of the light.
Yes, we did sorry, it went off. For this presentation, it was done like that. However, we never thought what information we could get when we put together those two measurements. And in my mind, I'm at the lower level at the moment. Perhaps we can talk about it later, what use case we would have for this application. And this is just the software development. It is nothing more, because hardware is already there, and even the ports in the sample chamber are already there. So we could have it combined, I believe. All right. If I'm not mistaken, the next on our schedule is lunch. So let's have it. Thank you very much.